wise. Okay, so now we've got some expressions for the capacitance for two common geometries. Let's move on and worry about these scenarios where we have multiple capacitors in circuits. So why might this be of relevance? The reality is sort of a practical thing here in two respects. Capacitors that you're starting to see are quite useful practical devices in electrical or electronic circuits. Their main use is energy storage, but as we'll see after the spring break, they also can be used to introduce some time-dependent phenomena in circuits. And so, practical stuff. We may want to have a particular value of energy storage, or we may want to have a particular time-dependent behavior in a circuit, which means we may want particular values of capacitance for certain applications. Now, on a practical basis, if you are going to a store and buying components to build electrical circuits, or you're building iPhones or whatever, you don't have access typically to any random value of capacitance. And so you may be forced to kind of make use of what you can obtain, buy, whatever, and see if you can then combine those units together in a way that actually produces for you the desired capacitance, okay? So there's a practical reason for that, just simply in terms of when you're buying these components, you can't get them in totally random values. And then there's also the feature that in reality, whether we like it or not, elements in electrical circuits or electronic circuits tend to have capacitance associated with them, even if we don't want them to, okay? Because there's charges being stored all over the place. These things are obviously extraordinarily complicated. There's electrical charges all over the place. And whether we want it or not, there are what we might call stray capacitances associated with complicated circuits. And so it becomes important for us to know how to handle situations where we do have multiple capacitances together in some sort of setup. So we're going to start out simple and build up in complexity and look at this question of combinations of capacitors. So we'll do a little bit of just standard understanding how this looks, depending on whether we have capacitors in what we call in a series configuration or in a parallel configuration. Probably most of you think you know very well what that means. Probably most of you do know pretty well what that means. But when you're confronted with a complicated circuit, it's sometimes less straightforward than you might imagine to figure out whether things are in series with one another or they're in parallel with one another. So let's start off with some simple setups for, to begin with, caps in parallel. And I don't know if I'm going to have enough space, but probably I will, so maybe I'll set this up over here for caps in series. And then once we peruse this and digest it a little bit, I'm going to give you a couple of examples to work through. So here might be a schematic representation of, in this case, 3 capacitors in parallel. So here we go. These are going to be set up, connected to some kind of source of potential difference. We still haven't quite defined what these are yet, but let's call it a battery for now. And at this point, we're pretty much going to drop adding deltas for potential differences, and I'm just going to say there's a potential difference V across here. And I'm going to label these capacitors C1, C2, and C3. Okay. So what does parallel mean? Many of you, I'm sure, have done this before, but I want to start getting used to looking at these symbolic representations of parts of electrical circuits. These lines are simply idealized conductors. They have 0 resistance. Again, we'll talk more about this after the break. So these are just connecting elements. Here we have 3 capacitors. Okay. What do I mean by in parallel? It's basically the statement that if I look at a couple of points in a part of a circuit, maybe these 2 points, it's an answer to the question of how many ways, in this case passing through capacitors, can I get from point A, represented by my right hand, to point B, represented by my left hand. So clearly I can go through C1 directly, Again, these straight lines are just conducting connectors. They have no active function. So I can also go from right hand to left hand by going through C2, and of course I can also go through C3. So in this sense, there are three routes going from A to B, top finger to bottom finger, passing through capacitors. That's what we mean by in parallel. Okay? So these are most definitely in parallel. In a moment we'll talk about the contrast and looking at these in series. Okay, what can you tell me about the potential difference across each of these capacitors?
It's the same.
Yes. Okay. So, same potential difference across each capacitor, all capacitors. Okay, that's good. What can you say about the charge on each of these capacitors? Given what we first defined about the relationship, how we define capacitance, in fact, the relationship between charge and potential difference.
It's proportional to the capacitance.
So let's see, we had Q equals CV, right? So the charge on each is proportional to the capacitance on each. Good. So that means in general, if these C's are different, we're going to have different charges on these three capacitors. So I might, for example, have minus Q1 plus Q1 here, minus Q2 plus Q2, and so on. Yes, in general, since this is common for all of them, and they in general have different C values, they have different charges on their plates. What is the total charge? So let me make a statement about that first off. In general, different Q's on each capacitor, assuming they have different capacitances. Okay? What's the total charge stored in this three capacitor setup? Yeah. So you're right. What's the total charge stored on one set of plates, meaning either the upper ones or the lower ones? Smart, correct answer, but I asked a poorly phrased question. If we're just talking about, as we often are, what's the charge stored on a capacitor, we're usually talking about on one plate of the capacitor. So what's the total charge?
V brackets C1 times C1 plus.
Don't get too complicated yet. Just tell me in terms of the Q's.
The total charge would be VC1 plus.
Not yet, not yet. Just in terms of the individual Q's.
Q1, like.
Yes, much simpler than you want to tell me. But you're right.
In terms of
The individual Q's, what's the total charge? Okay, I've really messed that up. So,
Q1 plus Q2.
yeah, there you go.
Oh,
You were one step ahead of me, which was good, but I wanted to do this more stepwise. So of course that's the total charge, okay? Now, we're often interested in defining what we call an equivalent capacitance. So, this is the idea that we can replace the actual three capacitors C1, C2, C3 by a simple equivalent capacitance, which I'm going to call C equivalent, based on some of the parameters that we've determined. So C equivalent in this case should just be the total charge, this thing, divided by the potential difference across the whole thing. And so in this case, of course, it is simply, let me make sure I got this right. So this is just C1 plus C2 plus C3, right? So, pretty straightforward. I've got this separated out into individual constituents. And if I just divide this by B, I can write this as C1 plus C2 plus C3. Okay? So, quickly simpler. What has it told us? It tells us that this three capacitors in parallel can be replaced, and we'll often do this visually and simply draw it as such. So now we would write it simply like this, okay? So we're replacing it by a much simpler circuit where these three capacitors in parallel are replaced by this equivalent capacitance, which has a value which is simply the sum of the individual capacitances. Okay? Again, couldn't really disagree. So, what do we see here? The equivalent capacitance in this case is always bigger than the individual capacitances. Okay. No big deal. Everyone okay with that? Yeah.
Why is it negative charge connected?
Thank you. All the way around, right? Okay, thank you. Okay. So, a little bit more interesting for capacitors in series. We get a similarly concise but slightly different answer, of course. Let me highlight this because you're going to use it quite a bit. So it's that and that. And I guess the other things I want to highlight are those two statements. Okay. So let's now look at some capacitors in series. Let's go a little bit more space. In series. Okay, so let's take a similar setup now. And so I'm going to have a source of potential difference, V. And okay, let me draw it like this. We need a complete circuit, C1, C2, C3. Okay, so here's an example now of three capacitors in series. Okay, how do I know they're in series? I'm going to put my fingers in a couple of places that straddle the capacitors there and there. And the question to answer is how many ways going through capacitors, so don't worry about going through the battery, how many ways going through capacitors can I go from A, left finger, to B, right finger? How many ways can I go? One, okay? This defines things that are in series. There's a unique sole way of going from point A to point B, passing through those elements, capacitors in this case. We'll extend that to objects called resistors after the break. All right, so that's the setup. So those are three caps in series. I'm going to ask you to think about these two things now. Potential difference across each capacitor and the charge on each capacitor. This one requires slightly more deep thinking, but not very much. Let's say, because I'm kind of imagining now I've got this battery that's exerting a potential difference across all of these. Let's say that I end up with a plus Q on this and a minus Q on this. And look at where I'm drawing these things. These are the first sets of capacitor plates that the battery sees, in a sense. And so in the same way that our battery here is driving a charge asymmetry, in this case now corrected with sign, it's setting up, let's call it plus Q on here and minus Q on here. So think about now what this suggests about the charge distribution on these interior capacitor plates that are not directly connected to the battery, but of course they're connected via inductive effects, which is to say, the fact that I've got plus Q on here presumably has an effect on this, and so on and so forth. And remember that all of these lines here are conducting elements. So what does that tell you about the charge distribution sort of in the middle of this array of capacitors in series?
It's equal. Like the charge is equal, charge is equal on each capacitor.
Okay, that's correct. Can you explain for me how you get to that answer?
So the voltage on batteries is you say pulls and negatives away, so the plus is going to distribute itself in the top plate, and that's going to induce a negative to distribute in the bottom plate, and then that negative keeps pulling negatives away from the top plate to the next capacitor, which is just
Okay,
a
good.
chain reaction.
All right, so it's exactly the right thinking. So the fact that I put plus Q on here, again, yeah, this thing tracks negatives from this originally electrically neutral element here, it's all conductor. So So I have equal amounts of positives and negatives, detract negatives, and what's left, let's say, is plus Q here. That sort of thing that looks like a capital H is again all conductive, it's electrically neutral, but because I've got plus Q on here, it's going to tend to attract an equal and opposite charge to this plate. Again, this whole thing is electrically neutral, so I'd better have plus Q here, minus Q, plus Q, so on and so forth. So it sets up this ladder of equal and opposite charge pairings as we go along this series elements of the capacitor in the series. So what do we have in this case? We have the same Q, and just to clarify this again based on Ariel's question, what I mean here is the asymmetrical charge on each side of the capacitor, and just the magnitude. So we've got the same Q on all caps for this reason here. What about the potential differences across each capacitor now? Jessica?
They're proportional to the capacitance.
So are they proportional to the capacitance? So I've got the same Q everywhere, in principle different C's.
It's proportional to the inverse.
Right, so they're inversely proportional to the capacitances, right? But they're different in general. So, I guess they're inversely proportional. So now I have different V's on each capacitor. So here I've got the same and I've got different. So these are obviously the opposite way around to what I had on the case of caps that were in parallel. Okay? So keep those two sort of sets of statements in mind. They will be important as we go on and look at solving actual problems which we're about to do. So let's see what this looks like in terms of finding an equivalent capacitance. So, okay, what then is the total voltage across this 3 capacitor in series array? So again, you could be following things along here, but kind of inverting them if you want. Okay. So now that we see we're looking at the total voltage as being the sum of the individual voltage drops across each capacitor. And now we can lastly again define an equivalent capacitance. And if you think about the form of this, it looks like 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3. So there's a little bit more algebraic manipulation going in there, but you can easily see that this works out. So I'm just looking at adding the voltages and looking at V equals Q over C. I've got the same Q everywhere. That gives me this expression now, the equivalent capacitance for these 3 capacitors in series. Okay, questions on that? So,
It's the same, I guess, condition that the capacitance has to be different, or there could be different on each capacitor.
Sure. Sure.
Because it's
Yeah, this is, I mean, these are generally different, but of course if they're all the same, then I'm going to have, yes, I should have put if different.
yeah.
Yeah.
For the equivalent, so are you saying that these have a charge of Q? Like, why are we not having this?
Say that again.
For this case,
Yep.
it looks like if you're looking at the equivalent capacitor as a charge of Q, right, why do we not have like the req?
Why do we not have?
Like the req?
So I'm not worried about it. Well, what am I worried about? What I'm worried about is the charge on each capacitor. Yes, it's the same in this case, but what I'm trying to get to is a relationship between an equivalent capacitance. So again, I want to replace this with something that looks like, and I ought to be careful careful how I annotate this now. So this is now C equivalent in series, and this is C equivalent in parallel. My goal here is to get an expression for this. And so what I'm really looking at is, what can I say is the relationship that relates together the individual components with a total. Now in this case it's clearly the voltage drops. In this case it's clearly the charges. So that's relating the individual components with an overall equivalent single component. So that's the thing I'm going to need to make use of, and then I just plug in my usual Q equals CV expression to get what this should look like in each case. So what I care about is the thing that relates the individual components to the overall, what I'm assuming is the equivalent charge and voltage drop. So this is still Q on this equivalent capacitor, but then we've got made of it, in this case, 3 individual voltage drops. I don't know if that makes sense, but that's kind of, that's what's motivating this. Okay, so now we've got 2 expressions that allow us to combine capacitors either in series or in parallel. So the question is, what are we going to do with it? And the question is, for you, what are you going to do with it? Because now I want you to tackle these 2 problems. So the first one is a really straightforward warm-up, but the second one is way more involved, so much so that I'm not going to do all of it in class, but some amount of it. So I'm going to work through the first one with you. It's pretty easy. I should have left myself some space, which I did not, but okay. Let's just quickly talk through this one. I want to replace this 3 capacitor array by a single equivalent capacitance, and I want to know what its value is. Okay? I've not even given you a voltage across here, so we can't calculate very much beyond the equivalent capacitance. All right, so take a look at this. I've got these 2 and then this one off on the right. My strategy for simplifying these circuits, and you're going to be doing this in a somewhat stepwise manner. Of course, when you see something as complicated as that, you're going to have to break it down into subparts. But my inclination is always to look in sort of smaller subparts of a circuit and see what I can combine together in terms of equivalent capacitors, starting small and then building out. Okay? So, if you look at this, what's your first inclination of how you would simplify this? So I've got these 3. Yeah.
Find the CEQ just of the series.
These 2 guys.
Yeah.
Right. So I'm going to start in the middle, and you know, sometimes you may find that you want to kind of redraw the circuit at various stages to keep track of things, again, particularly in cases like this where it's complicated. In this case, we don't need to. Let's focus on these. I have C1 and C2 in series, right? If I look at those 2 points, and I'm looking at how many ways I can get from point A, left hand, point B, right hand, passing through those elements, 1 and 2, I can only go this route. These are clearly in series. So, my notation here to try and keep track of things is often something like this. Since they're in series, I expect to be using the inverse or reciprocal relationship. I might write something like C1, 2 to remind myself that I'm combining C1 and C2. And so in this case, it's just 1 over C1 plus 1 over C2. And if you like, you can put this in numerically. And in cases as complicated as this, it's probably one case in a class like this where I would actually maybe encourage you to put in numbers along the way. Otherwise, it gets pretty hard to carry all of the symbology in that case. In this case, it doesn't really matter, but what do we get if we put in numbers here? We've got 1 over 10 plus 1 over 5. What does that tell me for C1? Excuse me, C1, 2. Yeah. A little louder?
Is it 10/3 microfarad?
Let's see. So here I've got 1 over 10 plus 1 over 5. so I get this as, yes, 10/3. And now I've got C12, and again, here I've done it numerically. I might just have written this as C2 plus C1 over the product of these things and then flipped it, something like that. Fine, so now I've got this, and what you might want to do in more complicated problems is to simplify this visually, and so replace it by an equivalent single capacitance, now labeled C12 in this notation, so that it looks like this. Okay? And so you're kind of breaking each part down in the interior, replacing by an equivalent capacitance, and then looking at how that relates to its next neighbors. So this would be step 1. What about step 2 in this case? Yeah. Right, so these two are now in parallel. And again, if you are finding this necessary or helpful in the early stages and you practice this, ask yourself how many ways are there to go from point A to point B, passing through the elements that we're looking at now. So I can go either this way or I can go this way. So these are two capacitors now in parallel. And so in this sense, and again, my notation here might be something like the following: C1, 2, 3. Since these are in parallel, I'm going to add them in straight summation. C1, 2 plus C3. And we obviously have values here that I can simply plug in, and I get a total equivalent capacitance. And again, eventually, I might visually simplify my life by making it look like this. Okay. So this one's a fairly straightforward problem. It only has 3 elements in it. This one, by contrast, is way more complicated. So I'm going to ask you guys to work for a few minutes with your neighbors on this. Let me just set it up to make sure we've got all the ingredients. Yeah, sorry.
You have C3 equals C4,
Yeah.
which is 4, and then C2 equals C4, which is 2.
One of them's supposed to be
Yeah,
C5.
Okay. What did I really mean here? I meant C3 equals C5. Thank you. Okay. So, this is an example of about as tricky a capacitor problem as you might ever see. So let's just quickly set it up, and then I'm going to let you guys work on it for a few minutes. So there are 6 capacitors in a somewhat complicated setup. Obviously have numerical values, which in this case I would suggest using, because otherwise the algebra becomes pretty onerous. We have a potential difference applied by a battery, and so at this point in principle we should be able to figure out for every component what the charge and potential difference across its capacitor plates is. Okay? So, the first step, I'm going to ask you to simplify this and come up with an equivalent capacitance, a single capacitance. The implication being that I can do that I can simplify that 6 capacitor array into a single equivalent capacitance. I want you to tell me what it is. Then I want you to tell me what the total charge across that equivalent capacitance is. And then the more tricky part is, having simplified it to get those first 2 answers, you're going to go back and complicate it again, in the sense that you're going to go back and then sort of look at each individual component to figure out what charges and potential differences are on those components. Questions before you guys work on that for a few minutes? Okay, go. And please do talk to your neighbors. I'm trying to really encourage that peer work, and we'll be continuing to do so in presentation. Okay, so we're going to give you 5 or so minutes. It may actually take us almost to the end of today's class, but it's a really important skill to be picking up. So yeah, please talk to somebody.
Okay, the one in series is 5 and 3, which is 1/4 plus 1/4, 1/2 is 2. So together this is 2. And then we're just gonna add this up. So okay, these are just. Are we sure these are like nothing about this screws up their parallel?
No.
Okay, so I know that's 2. Then we can do C4.